Okay, our next presentation is by Rohan Naidu, talking about into the first billion years with the James Webb Space Telescope.
Yeah, good afternoon. My name is Rohan Naidu. I'm a second-year fellow. Today afternoon, I'm excited to regale you with tales from the first billion years of the universe that we are seeing for the first time thanks to JWST. Before I start, I want to thank Neil and Jane for their personal touch in this fellowship and really making me feel welcome in the community. One thing you often hear as a postdoc is that it's a very tough period of academic life. It's very isolating. But it's been such a privilege to be part of the Pappalardo community and part of the family, really. And I truly value that. I also really value the independence of the fellowship that has really allowed me, as you'll see, to really dream big and build big experiments and really work in a very free and independent manner. So thank you for that. I always like to set the stage with one of my favorite plots in astrophysics because it just quite literally contains everything. It contains the entire history of the universe. So on the far left there, we're starting off with the Big Bang, the afterglow of the Big Bang, the cosmic microwave background. And shortly after the Big Bang, the universe is plunged into darkness, right? It's a gigantic, cold, lifeless ocean of neutral hydrogen that you have here in this period that we call the cosmic dark ages. Following that, you see these tiny pinpricks of light that begin to come to life. These are the first stars and the first galaxies that are making their presence known in this cold, dark ocean by blowing these fronts of ionization around them. Their heat is carving out these bubbles in the early universe. Eventually, these bubbles coalesce in this really grand period of transformation. And finally, today, we're sitting in a galaxy like this one, trying to make sense of everything that has come before us. So this whole story that I just told you, while grandly hypothesized and theorized and imagined, till very recently was still yet to be directly observed. And that is what today's talk is about how we are finally piercing the veil and looking directly into this very first billion years of the universe, where all these profound events happen for the first time, and the chain of events that would someday lead to us sitting here in this auditorium and puzzling this over. The first link of that chain first began here. As you all know, this talk is going to be about JWST, which was successfully launched on December 25th. This is my favorite image of JWST. It's the last image taken after the launch shuttle basically parted from the machine and sent it away on its journey 1 million miles away. I recently was able to talk to a scientist who was present in the room with President Biden when he released these images for the first time. And so President Biden, turns out, was very delighted by these images, but he was desperate to know what hypothesis we were going to test. All this was pretty and beautiful, but what is the experiment that we're conducting, and what are we going to learn? And what JWST was really built for was to reveal the very first generations of galaxies. So galaxies like this one over here, this tiny pinprick of light that you might be familiar with from my talk last year that I'm going to give you an update on. Galaxies like this that are so distant and so far away in the early universe, all their light, by the time it makes it to us, is visible only in the infrared. So here I'm showing you JWST images in various wavelengths. So 090 is 0.9 micron, 1.1 micron, all the way to 4.5 micron. So this galaxy, based on our previous facilities, was just completely invisible. There was no way we could see it. But now, finally, with JWST, it shows up. And this is because all its light is redshifted into the infrared because the universe is expanding. And also, all the blue photons from sources like these are completely absorbed by these vast oceans of hydrogen that we were just talking about. It completely soaks up all these blue photons. And so you really needed to build JWST to reveal this first generation of galaxies. And so right in the very first images that President Biden released and that we saw, galaxies like this became very apparent. And the mystery that I told you about last time was that in these very first data, we were already able to find galaxies at record-breaking distances that were much more luminous and potentially much more massive than all our models predicted. And this really was a cause of great excitement across the community, because how was the universe able to form things that were so bright and so big so quickly? In the year and a half since then, we've really gone through about a year and a half of JWST data. Galaxies like these keep cropping up everywhere we look. So here I'm quantifying that. I'm showing you a sense for how many galaxies we are counting as a function of how bright they are. And so these types of galaxies show up on this corner of the plot, where you see I'm plotting how their number densities are basically more than a factor of 10 or a factor of 100 higher than all our state-of-the-art simulations and models predicted prior to JWST's launch. And so this really has been an animating question in the community about how do we form these galaxies so early, what are their properties, how do we make them? And if you're not if your language of preference is not numbers and figures, but baby pictures, your mental model for what's happening is that we went in with JWST hoping to find tiny little babies that were just celebrating their first Diwali with their grandparents. But instead, you found the equivalents of astronomy, PhD graduates, and degree holders already. And so again, to give you a concrete example of how much interest Neil takes in the fellows, last Christmas when I showed up for the signature Pappalardo Christmas lunch, Neil had this article from the Scientific American folded on his table, and the minute I walked in, he started waving it and wanted to talk about it. Because the first word of this article says something like, Rohan Naidu was sitting in his pajamas when he found the galaxy that may have broken cosmology. And since then, Neil has wanted to know, have these galaxies really broken cosmology? Did they turn out to be at these very large distances? And so those are the pieces of the puzzle that have come together this year. Till now, I was showing you images like these, where we really are averaging, we're collecting light in giant buckets of wavelength, right? So we're collecting all the light that exists basically between 0.8 to 1 micron, or 4 to 5 micron. And what we really want to do, and what we've been able to achieve in the last year, is spectroscopy for these sources, where we really are able to break up the light into very, very fine bins. And what you see here are imprints of chemical elements. So you see lines from carbon, you see lines from nitrogen, from oxygen. And this really is data that has moved. I was at a conference recently, and one of the most senior and decorated astronomers in my field was saying how looking at this kind of spectrum really made her weep when she first saw this plot. Just because of how profound it is that we're able to measure lines like these, not in a local galaxy in our backyard, but a galaxy sitting really at the very brink of space-time, one of the farthest beacons in space that we've ever discovered, merely a few hundreds of millions of years after the Big Bang. And we see the same chemical fingerprints that we're used to in galaxies close by, but shifted so far away. So this spectrum confirms that these galaxies that we're finding in these early data really lie at these large distances that are so early in the universe. Furthermore, they show fingerprints of all these chemical elements telling us that the kind of carbon and nitrogen and oxygen that would one day give rise to life on Earth here was already in place, at least in this system, in a matter of a mere few hundred million years after the Big Bang. So this was the first such galaxy in that class of very bright and very distant galaxies that was confirmed. As of today, it is the most distant source in which we have detected such lines. And it raises many more questions than it answers, right? So there have been over 100 papers trying to explain what's going on with these sources. And after getting this data, it seems that the number of explanations has only exploded instead of collapsing. We think that there could be a very compact and very vigorous starburst in these galaxies. Potentially, there is already a black hole that is producing all this light. We might be seeing globular clusters forming in these galaxies. We could also potentially be seeing stars that are being shredded apart. And so you really are seeing the remains of them, tidal disruption events that are producing this brightness. So a key piece of the puzzle that I'm hoping to put into place this year is to really go from this one galaxy that we've gotten this really beautiful data for to several more. So for about 1.5 days this coming year, JWST will hunt for about 15 luminous such galaxies at my behest. I was very fortunate to have a program approved for this cycle of observations, where we really are going to go after several of these really, really bright galaxies at these extremely high redshifts to test what's inside them, right? Like, do all of them also show so many of these chemical elements? How many of these are real? And so this is data that's going to come in very soon, roughly October. And so these are the types of galaxies we're going to target in this program. This is the largest sample of them collected across all the JWST data that's been taken till now. We've put together the most promising candidates, and we're going to go get those kinds of spectra that brought really senior astronomers to tears. We're going to get hopefully, like go from 0 to 1 to 10. So this source, for example, is one of my favorites from this sample. It's one of the brightest ones, potentially consistent with the redshift out to about 13, 14, 15. You see this, again, characteristic feature of being extremely bright at these infrared wavelengths and then completely disappearing into these upper limits. So stay tuned for getting potentially 10 more of these objects very soon. And so that's my update on your question of whether these galaxies really are far away and what's in them. For the rest of my talk, I want to talk about the other major surprise that has really galvanized the community and really surprised us about the first billion years. It's about this class of objects that we're calling the little red dots. So if you look at pretty much any JWST image, you find roughly one of these extremely compact, very red sources that really just stand out. If you just are scrolling through them, they just pop out as being among the most brightest and striking objects at JWST wavelengths. I couldn't resist putting this in, Matthew, because I wanted to tell you that we're continuing the tradition of Pappalardo fellows in Quanta magazine. And so this stack of little red dots, as is, was featured in Quanta magazine's roundup of discoveries last year. And so when we went and looked at these little red dots with spectroscopy, we found this, yeah? So we found all of them basically had these extremely broad features that I'll tell you in a second. But it's really amazing how concordant they are in terms of having these very, very broad wings when you look at their Balmer lines with spectroscopy. So what's going on here in these little red dots, we think, is that they're essentially harboring extremely massive black holes. So the kinds of objects that Erin Kara and Rob Simcoe and Christina Eiler study, but baby versions of them. So what we're seeing here is the accretion disk around the black hole is producing these extremely broad features in these Balmer lines. It's kind of ironic that some of these brightest objects actually contain these dark black holes within them. But what you're really seeing is this gas being really flung around these centers at such large velocities that they're producing these really spectacular and bright, broad lines. And to just put it into context in terms of what is really exciting us about these little red dots is that for the longest time, in the first billion years, we have known these really behemoth quasars, really, really massive black holes. These are the kinds of objects that Rob built fire to discover. And so here's a review that Rob led last year showing this entire compilation of really behemoth black holes. But one of the key open questions was, where did they come from? Were they born massive? Are there smaller variants of them? How do they build up so much mass in such a short time, barely after the Big Bang, when the universe is a few hundreds of millions of years old? And so we might be getting the beginning of an answer thanks to these little red dots. So what I'm showing you here, again, is number counts of objects as a function of how bright they are. And so these behemoth black holes that we were just talking about, that fire has discovered so many of on Magellan, the instrument that Rob built, these are the classical quasars with really, really massive black holes here. But now JWST is finding these little red dots in really enormous numbers, much more than any of us predicted or projected. and they seem to be really, really everywhere. And the reason they're discovered just now is because they were extremely, extremely faint beyond the reach of all the previous facilities we had. And so this really is brand new discovery space that JWST is opening up. And so, of course, as you can imagine, the press has enjoyed covering these very baby quasars. This is my favorite press release on this class of objects. And this is one of my favorite images of them, because what it shows is it shows one of these tiny little red dots up there in a corner somewhere here, along with a big blue dot, which are the really enormous quasars that we are used to studying. And so both of them are in the same picture, where the baby quasar and the big behemoth black holes are pictured together. On a personal note, I really enjoyed that we ended up naming this class of objects little red dots, because I did my undergraduate studies in Singapore at Yale and US College. And Singapore famously refers to itself as the little red dot. So that is what the country calls itself, because it's this tiny little nation surrounded by all these mighty neighbors, but you're still managing to punch above your weight. And that's exactly what's happening in these systems, where you have these tiny compact objects, but at their centers are these really powerful, massive black holes. And so again, to sum it up, what we really are finding is we are able to fill in these hidden chapters of black hole growth, where we knew these behemoths existed earlier, but now we are filling in these much, much lighter objects, where in their most incipient stages, you see that the star formation is still dominating these galaxies. You just have this tiny little black hole that's growing. But then eventually it begins to overwhelm the entire light in the entire galaxy, right? So these tiny little black holes end up outshining every single star in their galaxies, despite occupying such a tiny fraction of them. And the mental model here really is that we are seeing how these black holes go from their caterpillar stage into these cocoons that are full of dust and enshrouded gas. And then eventually, maybe they emerge as these butterflies shining bright and blue at us. But this very much is an open field, and whether this is an evolutionary sequence or we are seeing entirely new species of black holes at these high redshifts is very much an open question. One thing I would like to emphasize is that we already start thinking about what's coming next. And these discoveries have just made the Giant Magellan Telescope much more exciting than it already was, because all this bounty of really bright, unexpected sources we're finding at the highest redshifts will be within reach for the Giant Magellan Telescope, and we'll be able to characterize them in great detail, right? Because this really is the sort of spectroscopy you need to confirm things like the very first stars, like the POP3 stars that Anna Friebel and her group pursue, or confirming the masses and the very details of these very first black holes. We need to build a GMT, and we need to access this part of the spectra, whereas with JWST right now, we're just limited to these wavelengths. The note that I like to end all my JWST talks is that it's really not that long ago where we were debating whether other galaxies even exist, whether the Milky Way was just its own little island, right? And that was in the 1920s. Not far from here, there were the great debates taking place about our place in the universe. And only in the short span of 100 years, which is nothing compared to the spans of billions of years we're talking about, we have gone from debating that to really pushing our cosmic frontier all the way back to the brink of the Big Bang, knocking at the very beginnings of time. And so, yeah, that's my summary, and thank you so much for listening.
Thanks, Rohan. Floor is open for questions. Neil, would you like to do the traditional first question?
Thank you, Rohan. When you look at all of the red dots, are the ones with black holes greater than 50% or less than 50%?
Yeah, that's a very astute question, Neil. This definition...
I'm only asking in a sense, what comes first?
Yep. Yeah, no, that's a great question. This is something that's causing a lot of confusion in the community as well at the moment. The way we defined these objects in our discovery paper was we actually searched for objects with broad lines, and then we found that basically all of them were little red dots. But if you made the selection first, if you asked for things that are compact and red at JWST wavelengths, and then asked what they were, a good fraction of them are these supermassive black holes. But you also find brown dwarfs in our own galaxy, the kind of the cooler cousins of the stars that Juliana is looking for planets around. You also find some compact star-forming galaxies, really compact sources that are that are just basically a bunch of star clusters together and that are really bursting. So they're red for very different reasons because of their star formation, whereas these galaxies are red because of these accretion disks and a lot of the dust and these very broad lines that we're seeing. So that's incredibly astute, and more astronomers, if they paid attention to this distinction, we would avoid a lot of confusion in the current literature. So thank you for that.
Other questions? Sava?
Thank you for the talk. The galaxy at Z of 12 point something, is the data precise enough and the theory good enough to guess how many generations of supernovae you must have had to have the anything heavier than helium?
Yeah, no, that's a really good question. We don't think this is a very primordial galaxy at all in terms of its chemical enrichment. So there have been several generations of type 2 supernovae in this galaxy already, right? The type 1 yields are not kicking in yet because of the delay time distribution that, of course, you know very well. But in terms of type 2 yields, this galaxy is already, it's nowhere where Anna Friebel's stars with all these primordial abundances where you really can count that, there's been these many potential POP3 and POP2 supernovae. This one's much more enriched, right? So it's more of a metallicity close to -1.5. So it's, which is fine, given that it is also expected to be so massive, right? It's more than 10 power 9 solar masses. It's kind of the Large Magellanic Cloud in terms of its stellar mass. So it is quite chemically enriched. So there's been several generations. But one of the surveys that I'm currently one of the PIs of is focused on finding systems that are extremely tiny, that are lensed by a gravitational lensing field, where we are hoping to find objects that are enriched just immediately by 1 or 2 generations of stars, and we should be able to tell that apart. So stay tuned.
Other questions? We learn as recitation instructors to just wait because there'll always be a question eventually. Wolfgang.
So you mentioned that those discoveries can maybe change our understanding of early, evolution of the universe. What is what kind of beliefs you think will be shattered, or if you think in a most radical way, how much could we have been wrong, or what are the assumptions or conclusions people have drawn so far, and you would think they are now really become questionable and are put to the test?
Yeah, no, thank you so much for the question. There have been papers written about all kinds of ways that all kinds of things that you can tweak with to produce galaxies much earlier, right? But I think the solutions that seem much more plausible on the table right now, the small tweaks that we need to make, are in terms of how bursty early star formation can be, where star formation just doesn't proceed in a very smooth and continuous manner, but in these really extraordinary bursts where you have star formation happening at a rate that is something 1,000 or 10,000 times what we're used to in the Milky Way in a very short and quick period. And that is something that a lot of our models were missing prior to JWST. So there are things like that seem much more plausible in terms of tweaking, but there are also things people have proposed models of like early dark energy that like, change the mapping between redshift and how much time you have in the universe to like grow early structure quickly. So those are sorts of the things people are thinking about. But I think a lot of the revolution in our understanding or like the modifications we need to make really have to do with how we think primordial star formation occurs, the modes in which it occurs, and like, a lot of these like early objects at very low metallicity that we are finding.
Yeah.
Great talk, Rohan. Quick question. Has anyone ran the numbers on what's the aperture size you would need to be able to probe ionized galaxies? Like, is that a crazy, ridiculous, large telescope?
Yeah, so to rephrase, to like look at individual like POP3 stars and POP3 complexes.
Or earlier version, or earlier galaxies. Because you mentioned these are enriched, so can we look for something that's less enriched with a next generation telescope?
Yeah, so I think the problem there really is in terms of like whether the universe can make these or not. Because in principle, JWST has the power to detect objects even out to redshift 16, 17, 18, 19, 20, like right to the point where we think things should form in the very first place, right, as agglomerations. But there's also people who dream about detecting individual like POP3 star complexes, individual stars. And people have done the calculations for this. So what we need is we need an order like 40-ish meter telescope, and we need to put it on the moon. And so, if we can do that, yeah, we're in the games. But even before that, I'm very optimistic with JWST that if we survey enough gravitational lensing clusters, so enormous clusters, the kind that Mike McDonald and his group study, that bend the light behind them, we might get lucky and see the sorts of things that you're asking about already. So we just need to be smart with how we're surveying with JWST.
So Rohan, just to follow up on that, so the big surprise is that you're finding these very massive cores at these high redshifts, and as you're saying, these are already enriched. But you're also saying JWST has the ability to go even further back. Is it surprising then that you haven't seen higher redshift things with lower masses, or is it just that you haven't had enough time with the data yet?
Yeah, no, to be clear, I've focused on the surprising populations at these redshifts, but already at redshift 10, 11, 12, when you go to lower and lower mass objects, we start seeing things that have currently the record is at about 100 the metals that we have in the sun today. So already at these redshifts, pushing to smaller and smaller and lower mass galaxies should get us to primordial chemistry, but also going to higher redshifts is also the way to do that, of course. Yeah.
Okay, let's thank Rohan again.